Hello, everyone. I'm Dr. Quentin Bailey from Embry-Riddle Aeronautical University, and I'm going to be introducing our speaker today. I'm the Department Chair of Physics and Astronomy here, and on behalf of Embry-Riddle, Prescott, and the Jim and Linda Lee Planetarium, I want to welcome everyone. We have quite a few people watching on YouTube, and we're very excited about that. So let me say a few words about our speaker today. So Dr. Erik Lentz will be speaking for us. And I first met Erik a while ago, back in 2007, when I started at Embry-Riddle Prescott as a professor. Erik graduated in 2009 with a space physics degree and went on to graduate school at the University of Washington and in Seattle. And he got his PhD in theoretical physics there around about 2017. And went on to do a postdoc at the University of Göttingen in Germany. And he's been working on theoretical physics, has quite a few published papers in his time in theoretical physics. And he's going to talk to us today about one of his recent papers, which is certainly a topic of interest in popular science and also in the literature. And so this is all about breaking the warp barrier, talking about special solutions to Einstein's field equations and trying to realize some kind of superluminal travel. So with that said, I think I'm going to turn it over now to Dr. Erik Lentz so that he can give us this very exciting and excellent talk.
Thank you, Quentin. Thank you for the introduction. And hello, everyone. I'm really excited to give this talk here at Embry-Riddle, my alma mater. This specific talk, actually thinking about exotic propulsion and wanting to research exotic propulsion was a large reason of why I went to Embry-Riddle for my undergraduate education, because they had just opened a degree program in space physics where you could specialize in exotic propulsion systems. And so in my time at Embry-Riddle, I was exposed to a lot of very interesting ideas. I learned a lot about general relativity, actually from Dr. Quentin Bailey, a lot about exotic propulsion systems, and I was very much interested in faster than light travel then. And during my 4 years there, I went from thinking that this type of project was just maybe a few steps away from advanced engineering to realizing through more and more study that it was closer and closer to a real fundamental physics problem. But I kept my interest in it, and fast forward a decade to when I was working as a postdoc at the Georg August Universität Göttingen. About the time that the lockdown started for the COVID-19 pandemic. And with everything shut down, I found myself with a lot of free time on my hands, and remembered this project that I had wanted to do for a good amount of time, and thought, well, this is as good a time as any, so why not? And my talk today is largely on what I've found out since then, after revisiting this topic and seeing if there's anything new to be found, any loopholes to be found to maybe bring this topic a little bit further away from science fiction. And this is essentially where I'm at right now. After a few months of study, I believe I have found a result that has been circulated both in the publication in Classical and Quantum Gravity, as well as online through other means, that contrary to popular belief in the literature, that it seemed to indicate that exotic means of media, exotic matter was needed in order to create solutions within general relativity that would allow for superluminal travel, that in fact general relativity does permit superluminal mechanisms that obey what's called the weak energy condition. Essentially, that means it only requires positive energy densities everywhere. and that in fact you don't need these exotic sources with negative energy density in order to make these hyperfast transportation mechanisms. And here in the figure, we have one view of one such solution that I found during my research. Here we're looking at two different components of what is called the shift vector, a component of the geometry of this particular soliton of space-time. Where in the left, we are looking at the component of the shift vector that is in the direction of travel, and on the right, we have the component that is pointing in the direction perpendicular to travel. And we'll go through the structure of this a few slides down the line. So the rest of the talk, I'm going to try and break down exactly the process I went through in order to make this very bold claim that was on the previous slide. I'll start by recapping some of my motivation, discuss what actually is a warp drive, what are some of the problems with the original literature of the warp drive, this negative energy problem being one of them, and where I began to see some opportunities for finding positive energy versions of these superluminal mechanisms. Get into the specifics of the particular method that I chose, using something called a hyperbolic shift vector potential, and then looking at one particular example, positive energy soliton, and wrap up with some hopes for the future. So, as I mentioned on the title slide, I've been interested in space travel for a number of years, and after reading way too much science fiction and actually reading some actual science and becoming more and more well-versed in the technical literature, I came to the conclusion, as many of us have, that near-term technology, in order to reach, say, our nearest stellar neighbor, Proxima Centauri, would require a monumental multi-generational effort. For example, if we were to try and use chemical rockets as a provider of propellant and thrust, it would take tens of thousands of years to go from our solar system to whatever planets may surround Proxima Centauri. We can do a couple order of magnitudes better if we look at nuclear technologies. We can, in fact, get down to on the order of 100 years for that same trip, still a multi-generational effort. And I came to the opinion that in order for interstellar travel to really thrive, one would have to be able to see both the beginning and end result of that travel. So it would have to occur within the lifetime of one human being, not just the one necessarily that would be on the ship, but also those back on Earth. And so that we're confronted with this speed of light barrier in order not just to get from point A to point B very quickly, but to do so in the attention span of somebody like myself. So we started thinking about ways that you could possibly move faster than the speed of light without breaking the rules of physics. And you might think that that statement, faster than light, is already breaking the rules of physics as we understand it. We'll mostly be talking about physical theories in the context of the general relativistic principle of space and time and gravity. You may have heard that no objects cannot move faster than the speed of light, and you'd be largely right. More specifically, what the special relativistic principle says is that two objects cannot move relative to one another through the speed of light, or locally, if we want to look at the general relativistic principle, cannot move past each other through space and time faster than the speed of light. However, you can move objects that are separate from one another to different points in space-time away from each other at speeds that much exceed the speed of light. For example, this model of cosmological inflation that we have for the early universe, reasons for homogeneity in the early universe, would take two objects that would have been in causal contact with one another and expand them through some physics during this inflationary period so fast away from each other that they would fall behind, from one's perspective or the other, a horizon. They would fall out of causal contact. They would be effectively moving faster than the speed of light away from one another. And so general relativity does permit certain types of superluminal travel so long as we're talking about global properties of the space-time. And so several mechanisms have been constructed in the past, warp drives being one of them, wormholes being another, for ways that you can get around seemingly this cosmic speed limit. And so we'll concentrate for this talk on the warp drive concept, which is exemplified by this picture of the expansion and contraction, this very famous sort of traveling wave picture of the Alcubierre, which has also been annotated by some little football-shaped ship and a torus, which is supposed to represent the where the primary source of the energy density would be in order to source this space-time. Right. But what is a warp drive? Well, after reviewing the literature, it seems like there's no formal definition for what a warp drive is. But for the purposes of this talk, we will take a warp drive to mean a soliton of space-time curvature that can move with arbitrary speed. And by soliton, I just mean a compact, as in has a finite extent, size wave that moves without changing shape from through time. And how we're going to describe those solitons is using how we're going to describe the geometry of these spacetimes is using a decomposition of the spacetime metric via the what's called the ADM formalism, which is essentially a decomposition of the four-dimensional space-time into foliations, essentially layers of time. So you will have three-dimensional surfaces. It's like layers on a cake. Essentially, you have this entire cake structure, but each layer is described by a particular value of this parameter time. And as we move up the layers of the cake, we are moving upward in layers of time. And so here we have our first real formula, which is the line element that helps us describe the space-time metric, which are the coefficients to each of these little forms, these differential forms, which are going to be described by a number of functions. This function n without an index is what we're going to call the lapse function. These n's with an index, the index runs over values of x, y, and z, indicating different directions within this these hypersurfaces. And this is what we refer to as the shift vector. And we'll notice that as we look at other terms of the metric, that the shift vector also mixes both differential elements of space and time. And this last element here is the intrinsic metric of the hypersurfaces themselves. And so Alcubierre in 1994, looking at this decomposition, noticed that he could make some simplifications. Say he looked at a flat hypersurface and he looked at a lapse function of unity and noticed that he could take one of these components of the shift vector, give it a functional form that looks like a top hat, like this figure here, and that top hat could move through space-time given the value that's produced at the top of the top hat. And that speed could be made essentially arbitrary. It could be 0, it could be the speed of light, it could be 10 times the speed of light, etc. And the interesting thing about this solution is that you could also put a craft, or if you looked at the properties of what the top of this top hat looked like, they seemed very ideal for a craft. That you could put an observer, a time-like observer like you or me, who are just moving through time, and they would be free-falling and they would move along, staying right on top of the top of this top hat as it moved through space and time. So any observer, any ship or whatnot that you would put it in this top hat wouldn't experience very high accelerations. They wouldn't be pulled this way and that. They would essentially just be in free fall the entire time. But around them, they would be moving relative to places outside of this soliton structure with potentially arbitrary speed. But there were some problems with this initial formulation, namely that it required a type of stress energy that we didn't know how to make, namely sources of energy with energy density, where we're used to things with matter density. We measure things with kilograms per meter cubed of matter density, which we can then easily convert to energy density. We would actually require something with negative kilograms per meter cubed types of energy density. Not just a little bit of it, but actually quite a lot of it. That if we were to try and create one of these alcubierre type metrics using natural phenomena, you can theoretically, using quantum principles, create areas with relatively negative energy densities using something called a Casimir effect. If you create a very small confined space that is isolated from the rest of space-time, and you could do something similar to this with the boundary of the alcubierre warp bubble being the edges of this top hat. Right, but if you made that boundary thin enough such that these negative energy densities would naturally arise, the actual amount of energy that you require would be very, very large. In fact, for a soliton the size of a 100-meter radius, you would require orders of magnitude more energy than there was in the visible universe. So not a very practical means of getting around. Here we have the general form for the Eulerian energy density of this ADM spacetime, where R is the Ricci curvature scalar for the three-dimensional hypersurface, and K is our extrinsic curvature, which appears in the energy term in two different forms, one being the trace of the matrix product of two extrinsic curvatures, and the other the trace of the extrinsic curvature squared. Now note that there is a sign difference between each of these terms. The intrinsic curvature, which we're going to essentially take to be trivial for the purposes of this talk, is positive. The first k dot k term is negative, but the last term, the k squared, is positive in sign. And if you were to take this form and plug in the alcubierre metric, you would find that only terms from this form would dominate the energy density, and you'd get something, if you were to carry out the algebra with the shift vectors that we discussed in the metric of the previous slide, you'd get something that looks like this, that it has to be, obviously, it's a negative definite operator that we're dealing with, that you're always going to require for solutions like the alcubierre type. You're always going to have negative energy densities. There were other warp drives that were created, namely here, one by Jose Notario some years later, that in fact didn't require large amounts of, well, it constrained the extrinsic curvature to be divergenceless, but still required strictly negative definite energies. Right, in fact, these statements were made a bit stronger with subsequent publications that by Olam in '99, Lobo and Crawford some years later, that stated, in fact, negative energy densities would be required for anything any spacetime that satisfied a superluminal condition. Right, so there have been some improvements in the energy requirements of some of these alcubierre or Notario-like drives, namely by invoking a mechanism, well, first by seeing that if you're to look at how the energy of one of these bubbles scales with its radius, that in fact you can drop the energy needed for one of these warp drive bubbles precipitously if you just make it smaller and smaller. In fact, you can make it somewhat reasonable if you make the size of the bubble microscopic. However, you can't quite fit in, a ship can't quite fit into a microscopic space. So another mechanism was invoked, saying that inside this bubble, outside here we have a small diagrammatic representation where this exterior annulus represents the alcubierre warp bubble. And inside we have this internal mechanism wherein you create a locally enlarged space. So you essentially make a bubble of enlarged space inside the exterior warp bubble, something that's big enough for a person or a ship to exist in. And this lowers the energy requirements precipitously. You can move down from orders of magnitude above the energy density of the universe down to solar scales or even down to kilogram scales, but you still require exotic forms of matter to do so, and still, much more than we have ever, say, theoretically created in a lab. And in fact, the mechanism for creating this locally enlarged bubble within the warp bubble also requires negative energy densities in the ways they've been proposed in order to create. So we still haven't gotten past this sign problem for the energy density. And so after reading all of this, reviewing the literature as I was sitting at home in March and April, I thought, well, what, if anything, has been missed? There's quite a body of literature saying that negative energy densities seem to be ubiquitous. In fact, they may be required. But I couldn't quite get past this term, the second positive definite term in the Eulerian energy density. And if I could conceive of a class of spacetimes that in which this third term would dominate over the second everywhere, then we're in business. So that is what I decided to try and do, to see if such a class of spacetimes existed. Here we have an expansion of that same Eulerian energy density in terms of the shift vectors and their derivatives. Namely, here we have there's a little bit of algebraic simplification has occurred, but essentially we see that there are three terms left over from this trace of k squared that you saw on the previous slide that are of indeterminate sign, that they comprise two multiples of different components of the shift vector that have derivatives taken in different directions. So they're not necessarily positive or negative to start. And here we, in the second line, we have three terms left over from the trace of the k dot k term, which are all negative definite. And so after this little bit of algebra, we see that the problem is now distilled down to, can we make these three terms everywhere dominate over the second set of three? And there would be our island of opportunity for creating possible mechanisms for transport. This is where we would make these positive energy solitons. And so after a little bit more thinking of what classes of spacetimes had been explored and which ones might remain to be explored, I noticed that given relations between these three components of the shift vector, there had been two sets of relations between them that had been explored and two that had yet to be, namely a linear relation between the components, or simply put, just having one component, namely in the direction of travel, non-zero of the three component shift vector. Also, the elliptic relations had been investigated some via notatio with this divergenceless relation of the shift vector components, but parabolic and hyperbolic relations between the components of the shift vector hadn't really been pursued, at least none that were present in the literature. And so I decided to, after some time, to go forward with thinking about specifically the hyperbolic relationship between shift vector components. Although I did spend some time thinking about the parabolic relationship, and I think there's still some promise there, but I didn't pursue it to quite the same degree. So that's still an open area. And this is how I formulated the problem, thinking about hyperbolically related shift vector components. Namely, I wanted to first simplify the geometry sum to just a single degree of freedom. I didn't want to solve for 3 different functions at once. I wanted just to solve for one. And so I distilled all these 3 components down to a single potential function, where I could then derive the components of the shift vector via a simple gradient. So now I'm only solving for this potential function, and I'm going to create that hyperbolic relation I was talking about by having this potential function satisfy a wave equation. So specifically, a very simple linear wave equation where we have some, and this wave equation is just going to exist over the hypersurface because we're just talking about elements of this shift vector. There are only 3 components over this hypersurface. So when I talk about velocities and whatnot of this wave equation, this is not necessarily a physical velocity. This is essentially just a piece. This is just a piece of mathematics that I'm talking about. I'm just talking about this parameter, this VH parameter of the wave equation. Also, in constructing this relationship, you have the opportunity to introduce a source function, which I will call rho for the wave equation. All right. So if we simplify the geometry of these spacetimes using these relations, using this potential function, using this linear wave equation, relating different second derivatives of this potential function, we can simplify the energy condition to equation number 1. Now, it does look somewhat simpler, although it's not necessarily easy to tell whether or not the sign is strictly positive, or if you can also have negative regions within space-time of a particular type. So in order to make it a little bit more clear, I found that you could bound from below the form of this energy condition to this equation, which then you can expand using the Green's function of the linear wave equation to this form, namely so we could express this energy condition purely in terms of this source function rho, as it appears in this integral function, as well as out in the coefficient at front. And after thinking about this expression number 3 for a little bit of time, I began to see that I could construct additional rules on the types of spacetimes that I would want to create, such that if we not only use this potential function, not only did we use this linear wave equation, but if we also employed these rules, we would then be solving for spacetimes that were only required positive energy densities as their source. And that particular rule that I came up with for this instance was that for a particular point in our space-time, that the source function, this mathematical object of the source function, would have to have the sign that was the same as the integral along this past wave cone being some piece of jargon that you pick up when solving for these wave equations. The past wave cone of this point, the integral of the partial derivative of this source function. So if both of these objects had the same sign, which we can see are these 2 different parts of this bounded from below expression for the energy, then whether they're negative or negative, positive or positive, 0 or 0, it would always be non-negative. And so now, with all of this structure in place, we can begin to construct new spacetimes with purely positive energy densities that could possibly travel at arbitrary speeds, and then begin to investigate their other properties. And so here, for the next few slides, I'll be going over the structure of one such example soliton. So for clarity, that parameter, that VH parameter, I have set to a numerical value of 10 for this particular example. So here we've constructed one such spacetime, and this first plot is of the source function, this source function rho. And so this isn't necessarily an element of the geometry. It is just a convenient means of setting the building blocks for constructing one of these solitons. And so what I did is I constructed in sort of this diamond formation a collection of the trapezoidal little modular collections of this source function rho, both with positive sign and negative sign, green being positive, pink being negative, such that the vectors that would be emitted from these sources via this wave equation relationship that they all satisfied would be confined to a nice compact region within this overall diamond shape. And so here we have those shift vectors. Again, this is the first figure that I showed on the second slide of this deck. And here we have what the shift vector in line with the direction of motion, which for your reference, the soliton here is moving to screen right. Here we have the component that is in that direction of motion. And blue is the direction aligned with the direction of motion for that soliton. So blue here is also moving to screen right, and red is a shift vector that is pointing to screen left for this particular panel. So we'll notice that this soliton looks vastly different than what we saw with the alcubierre shift vector. We no longer just have a single nice top hat function. We have a number of domains both pointing in the direction of motion and against the direction of motion. And if we look at the other component, the transverse component to the direction of motion component of the shift vector, we also see that we have portions of the shift vector that are pointing to the left and to the right of the direction of motion. Also, if we were to integrate the total amount of shift vector in each direction over the entire soliton, we would find that the total shift vector is 0, as opposed to the net non-zero shift vector that we would expect with this top hat function. So already a number of properties that are different from the alcubierre solution. Here is a plot of the energy density over the entire soliton. We'll notice that it largely lines up with the sources, this this wave equation source, where it is non-zero is largely where we're going to see non-zero energies. They don't switch signs, the energies. We see that they're only positive energies here, but they are almost strictly tied to where we placed these source functions. And if you were to integrate the total amount of energy that you would need for a soliton of this fiducial size with radius of this interior region being on the order of 100 meters, and the thickness of these boundaries being on the order of 1 meter, you would get that the total mass equivalent necessary to build one of these things would be on the order of 1/10 of a solar mass. So still very, very large. Also, something that I forgot to mention on the previous slide is that like the alcubierre solution, where you had this nice flat top to the shift vector where you wouldn't experience many tidal forces, and you could put some sort of spacecraft. I also designed this soliton so that it could also carry some observers without the observers being subject to large tidal forces. And that region is contained here in the center of the soliton. All right, here's another view of the volume expansion factor, theta, which is essentially the trace of that extrinsic curvature quantity, which we've seen many times in the Alcubierre solution as this traveling wave that's seemingly pushing, that the craft would essentially ride across the cosmos, with one area of negative expansion or contraction of space in front and expansion of that hypersurface behind. But for this particular positive energy soliton, we see something that's a bit more complex. Not only do we see positive expansions of the hypersurface and contractions of that geometry, we see them essentially occurring all around wherever we would have our observers. They don't just occur one in front and one behind. They both occur in front and behind the central region of our soliton. Also, as we saw with the energy in the previous slide, that the much of the weight where we have the largest expansions and contractions also line up with where we have the largest amounts of energy density. This is in contrast to the Alcubierre solution, where the largest regions of expansion and contraction are largely devoid of energy density, positive or negative or anything. Most of the energy density required to source the spacetime is exactly, seemingly maximally separated from these expansions and contractions. In fact, it's right where the expansion and contraction fall to zero. So another area where these two types of solitons seem to differ in structure. One of the last figures I'm going to show is of what is called the trace condition. Essentially, this is a figure of the total four-dimensional Ricci curvature scalar of our soliton. This is also sometimes referred to as the trace energy condition, even though it's not a really strict energy condition. And for our particular soliton, we see that we have both regions of positive and negative space-time curvature, total contracted space-time curvature. And in terms of relating this to perhaps the types of stress energy sources that we might want to use in order to create one of these solitons, that this four-dimensional Ricci curvature trace coincides with a certain combination of, say, a hydrodynamic fluid's energy density and pressure density, such that if you were to try to look at the equation of state for that fluid, you would see that it would dynamically change between being very non-relativistic and having relativistic motion, being very hot and having the constituent particles within it moving at locally very near the speed of light. There we go. A couple more comments about the potential physics of a sourcing plasma. This is something that I very much would like to pursue in the future, but solving precisely for the configuration of electric and magnetic fields and the energy densities and all of the other constituent relations that go along with it is a very computationally intensive step to take. So it's something that I'd like to do, but it wasn't necessarily within the scope of this first paper. But we can determine a few of its qualities, namely that in order for the soliton to be an actual soliton, that it is actually confined to a compact region at any one point in time, that it has to be electrically neutral. Otherwise, you would have some outleaking electric field that would drop off as 1 over r squared, and this would this very slow drop off would ruin the solitonic nature. It would mean that the actual energy density of this mechanism would not be compact. Also, we know that we have to have a very highly dynamic plasma. Not only does it in some locations need to be very hot, such that its constituents are semi-relativistic, but in other regions it also has to be quite cold. And that if we were to want to build one of these solitons in the next millennia, that we would probably want to bound the charge to mass ratio of the constituent plasma to something that we can create in large quantities, namely something like the ratio of the electron, the fundamental particle of the electron. All right. So for the next couple slides, I wanted to address some of the previous literature that has come out both in the past and in very recently, and how my solitons seem to fit within that literature. I mentioned about 10 slides ago that not only did the first warp drive solitons seem to require large amounts of negative energy density media, there also came about some papers that seemed to indicate that negative energy densities were required in order for these superluminal spacetimes to exist. These, Ullem in 1999, and as I mentioned, Lobo and Crawford in 2003, said that negative energy densities were unavoidable. Well, the soliton that I just showed you seems to circumvent that somehow. And so after thinking about how the nature of this proof and the nature of the soliton that I created, I noticed something rather interesting, that the proofs took a point-like limit of the spacetime. They required as a precondition that the spacetime had only a single fastest geodesic, single fastest path that they called superluminal, which means that the proof did not address extended objects like these solitons, like the one I made, or the typical way that you would approach the alcubierre solution. You'd give it some finite radius. However, if you were to take one of these solutions, like the alcubierre solution or the Notario solution, and take a point-like limit, so you only had a single interior point that was moving faster than the speed of light, you would find that the overall structure of these solitons was preserved, that you still had the region of the alcubierre spacetime, a region of locally contracted spacetime out in front and expanded spacetime out behind, and this infinitesimally small toroid of negative energy density to source it all. And so it seemed like this alcubierre spacetime fell into the purview of the Ullem, Lobo, and Crawford proofs. But if you were to try and perform a similar limit with the soliton that I exemplified, remember that the total shift vector of these solitons is 0. If you were to try and shrink one of these solitons, you would end up unraveling the entire shift vector structure. The entire soliton would collapse, and you would end up in this point-like limit with a flat spacetime. So it appears as though this type of solution, this type of positive energy soliton, does not obey the preconditions of the proofs. And that's my current stance on the matter at this point. Also, very recently, around the same time, another paper has come out titled Introducing Physical Warp Drives. And I've noticed online that there's been some confusion about the differences between these two papers. So I just wanted to take a minute or two to speak about how these two papers my paper and the paper by Alexei Bobrik and Gianni Martyr differ from one another. And I should also note that I've been in communications with these two gentlemen since the middle of last year, after my first paper went onto the archive, and I gave an early talk to the Centra Center in Lisbon, that we came into contact and we traded notes, and so I got to see an early version of this paper that just came out. And so, right, I wanted to talk about how these two solutions are similar and differ. Namely, the Bobrick and Martyr paper introduces a soliton that can move much like a warp drive, that is sourced only by positive energy sources. It is spherically symmetric. They specifically looked at spacetimes with some local rotational isometry in order to produce these positive energy solitons. But in order to, one of the restrictions that they found for these solutions is that they had to travel subluminal. They could not meet and surpass the speed of light. Whereas the solutions that I proposed can, like the alcubierre solutions, move at arbitrary speed. They can meet and surpass the speed of light while still, in this case, maintaining positive energy densities for their sources. They also looked at superluminal sources, a version of the alcubierre solution, and they put forth a mechanism for reducing the energy requirements of those solutions by reshaping the soliton from this spherically symmetric top hat function to something that's more oblate. So kind of like taking the sphere that is moving, say, off to screen right in this figure here, and beginning to compactify it, to shrink its dimension along the direction of travel. Interestingly, this is also a mechanism that I found in my own research, looking for the positive energy solitons as a way to reduce the energy requirement. And in fact, did use a similar mechanism in order to, in my final form of the soliton in my own paper. All right, so future work. There are still a lot of things to do, a lot of exciting opportunities to look at in terms of research, given this particular finding that we no longer need necessarily exotic forms of matter in order to make these hyperfast solitons. One of the next steps that I'd like to look at is means to reduce the energy requirements. Because as I said, for this modest-sized drive, you'd still require something on the order of many Jupiters in mass, or approaching something to a solar mass just to go up to the speed of light. So I'd like to get that down to something much, much more reasonable, so that you can try and reproduce these solutions in a lab, or potentially make one of these drives in some sort of real-world application. So one of the things that I'm thinking about right now is if it is possible to modify some of these mechanisms, say by the Vandenbroek or the Krasnikov mechanism of locally expanded bubble within the warp bubble type concept, to only require conventional physics, to only require these positive energy density sources, as opposed to requiring negative energy densities to make this locally expanded bubble, and place one of those bubbles inside of one of my own solitons. And if that can be done, or if some other novel mechanism can be created to do so, then we can start thinking about trying to create and detect one of these solitons in a lab. I'd also like to think about numerical aspects. What I've done so far has actually been relatively computationally simple. I managed to reduce the mathematics to just solving Green's functions, to just performing simple integrals, simple linear integrals even, in order to find these particular hyperfast solutions. But in order to do that, I had to avoid solving for the full dynamics of the system. I had to avoid solving for all of the plasma equations of motion, the Maxwell equations, etc. This really becomes a very complex problem very quickly from the one potential function that I managed to simplify it to out to dozens of degrees of freedom. But with further research and using the resources of today's numerical relativity plus hydrodynamics codes, it may be possible to include more and more of these degrees of freedom and more of the rich physics involved in order to make a full simulation, complete with a sourcing spacecraft, a place where your actual travelers might be located, as well as where you might be generating the power in order to source the type of plasma that would be required in order to make the warp bubble that would surround this particular craft. There are also a number of other interesting challenges that remain with these solitons, namely horizon problems and the like, that I'd also like to investigate both theoretically and numerically. So to wrap things up, hopefully I have been at least a little bit enlightening as to my thought process in finding these superluminal solitons within general relativity that appear to obey the weak energy condition and can be sourced by more conventional physics, and a little bit about my hopes for the future. So with that, I will say thank you very much for listening, and I'm ready to take any questions. So I believe I was instructed, and Erik, you can correct me on this, to bring up the chat. All right, so take me a few seconds. Okay. So I'll try to make sure to keep the volume down so we don't get an echo. All right. Okay. So, oh my goodness. It says there are many dozens of questions. Okay. Let's see if we can find a question. And Erik, if you have one already queued up, you can just hit me with it. Okay, so Erik just informed me that there is a question about what if we hit obstacles along the way, say something like an asteroid or even something like a hydrogen molecule, what would happen? It's a very good question. There's actually been some research about what would happen in the case of the alcubierre drives if the drive were to come in contact with some object, what the geodesic of that object, as from the perspective of the soliton, some object were to come in contact with it. And what has been found so far, at least for this type of solution, is that anything that, for sufficiently fast, say a superluminal version, an object would come to a standstill at the front of the bubble. And that this proposes a fairly interesting conundrum, is that if you have a superluminal alcubierre drive and you go any distance, you're accumulating all sorts of dust and gas and the like on the front of the bubble. And what happens to this energy? If you ever manage to stop, which there are other complications of that, but just imagine that we've gotten past those. If you were ever able to stop this alcubierre drive moving from superluminally to subluminally, these objects would then begin to move in a very coherent beam. And depending on how far you went, you'd have that much more energy built up on the front of your soliton. And so that could actually be potentially very destructive to any planet that you wanted to visit if you happened to be just if it happened to be just in front of you when you dropped to a subluminal speed. So it's a very interesting topic. Hopefully, we can solve that so that it doesn't have such disastrous consequences. Okay. Another question is, what is a soliton? Right. It's a very sophisticated sounding word for a fairly simple concept. Namely, it is a wave. It is a wave. Solitary means that it's by itself, in this case compact. It only takes up a finite amount of space. And it is a wave in that it maintains its shape and actually manages to move from one point to another with some constant velocity. So that's what is a soliton. Well, that would certainly be exciting. But I think it's even optimistically will be quite a number of years. I'm hesitant to say a lot because if you put a timeline out there, people will then try to hold you to it. But what I'll say now is that as far as there's some nearer term goals, more theoretical goals for research that I think can be completed or at least have come to some sort of conclusion within the next several years. Namely, most important in my mind is this reduction of the energy requirement. That is really crucial to being able to even test these sorts of solutions experimentally. And I think within the next few years, we should be able to come to some conclusion about whether or not we can reduce feasibly the energies from this solar mass scale down to something that we can actually construct in a lab. Something that's on a kilogram or gram or milligram scale is really what we need to get down to as far as the energy requirements. And also we can, if we're experimentally trying to confirm whether or not these sorts of solutions can exist, we don't necessarily have to go all out and look for something superluminal to start. We can start with something relatively small, so we can move from 100 meters down to, say, something that's the size of 10 centimeters. That drastically reduces the amount of energy by several orders of magnitude. And we can also slow it down. You don't necessarily want it to move too fast or it'll escape the lab rather quickly. So we might want the first solitons, if the signal's big enough, might be on the order of some kilometers per second in speed, something slow enough that we can sense it with good accuracy. And that also, that reduction of the energy, I don't know, I didn't really outline it very well, but if you noticed, the amount of energy required scales with the square of the velocity. So if we were to move from 300,000 kilometers per second down to, say, 3, that is a reduction of about 10 to the 10 orders, 10 to the 10 in energy right there. So 10 orders of magnitude. Right, did I answer the question? Timeline of development, right. So I think that energy question can be answered in the next few years. Then we need to find a mechanism for exactly how to create these. The solitons that I described here are very simple in that they are a soliton. They are moving with constant speed, but they've always been moving with constant speed. There was not a time where there was no soliton and then it collected and began moving and then maybe dissipated sometime later. It was always there. How did we get from some collection of matter, say out in space, to something that looked like a soliton and is moving with some speed is still a remaining question. Exactly how to do that and how to do that efficiently. That will probably also take a bit more time. And then we are at the stage of looking, and I think those two steps will be able to be completed within the next 5 years or so. At least, for one way or the other. And assuming successful result, we can then start to think about experimental verification. And that one is really tricky because depending on how you manage to reduce the energy requirements and how you manage to create these things will determine how easy or difficult it is to create one of these solitons in a lab. So this could be something that is a matter of years or a matter of decades to experimentally verify one way or another. Once that's complete, then we can start talking about actually building real-world prototypes. Mm-hmm. Yeah. Ooh. Sorry, I just realized you cannot hear the other Erik who's feeding me these questions. The question is, what would somebody inside the bubble see out in front of you? And that's a very good question. As you might guess, if the soliton is very slow, your view wouldn't change too terribly much. But as the soliton becomes faster and faster, and this curvature in front and to the sides of you would change, your view would also change quite dramatically. Precisely how, I have not done that calculation yet. I've thought about it some, whether or not you would necessarily see red or blue shifts or a contorting of, say, the starlight out in front of you. But that's a fairly difficult calculation to make because of the complexity of these curvatures, the complexity of this expansion factor. So imagine you have some light beam impinging on your soliton. It is both being contracted and expanded and can be deflected multiple times before it reaches you. And so it's a very interesting, complex question to answer. One that I would like to answer at one point, but unfortunately I don't have a full explanation for you right now. Causality, right. I've managed to avoid that so far by having a soliton, so we don't actually have, especially in the superluminal case, contact between travelers inside the soliton and those observers that might be outside the soliton. I imagine much like the twin paradox, which all of the interesting physics actually happens not necessarily in the travel time, because the twin paradox, you have two people that are the same age, twins, at the start of a journey. One goes on a trip, say to Proxima Centauri at very near the speed of light in a special relativistic framework, and then turns around and comes back and hasn't aged much, even though space-time is relative. And how do you know, from the perspective of the person who was technically on spacecraft, the other twin actually went on the trip. So how do you know which one would age and which one wouldn't? All the interesting physics, the solution to the paradox, is actually in the acceleration. The fact that they were both in the same frame of reference, and then one twin accelerated, so that it's distinguishable in that observer's experience. They accelerated both to get moving and to turn around. The analogy to this particular soliton is in the creation and acceleration of that soliton, as well as to create it in order to start on your trip, decelerate, reaccelerate, and come back. I imagine that's where all of the causality, the interesting causality physics will occur. But so far, I've managed, that hasn't necessarily been such a necessary exercise to go through, because so far with this soliton that has been moving ad infinitum, the two sets of observers haven't really been in communication with one another. So this is a specific plasma physics question about a particular type of high frequency pulse laser being able to create the type of plasma you would need. I do not have the answer to that. I do not have a plasma physics background. I would certainly like to learn more about plasmas and the type of plasmas that would be necessary in order to create one of these things. And how I plan to get there is first by performing numerical simulations of the plasma configuration of one of these solitons to determine the size of electric and magnetic fields, the equation of state necessary for the plasma at different portions of the soliton. And once you get an idea of the different dynamics that are necessary to create this soliton, then you can start talking about how to make one, what is technologically feasible at the moment. But I'm still a step away from that. Oh, say, right. Yeah, how much to say? The question is, when did I become, how did I become interested in this topic? And anything inspirational to say. So I'll say that growing up, as I think I mentioned in the beginning, I read a lot of science fiction. I watched a lot of science fiction. I was definitely a Trekkie growing up. And I became, very interested with the technology and the way I became very interested in that type of world. And one day, when I was, I think, about 10, I realized that someone had to make a lot of this technology that didn't exist, really. That someone had to make, all the interesting medical technology. Someone had to make a tricorder. Someone had to make a warp drive. And I decided I wanted to see if I could do that, see if I could make a warp drive. And I had, I had an interest in science or whatnot, but that gave me some direction. Even though, I could have picked something maybe a little bit more feasible. It was, I'd say about 10 is when I decided this was something that I wanted to see if it was possible or not, even if it did take a long time. And so I, having my mind set on that at all of 10 years old, I began trying to read more and learn more about the actual mathematics that would be needed to do this, the actual science, where the science was and where it wasn't. And of course, this took years. You didn't all do this then, but I eventually, over the course of, say, high school, became aware of Miguel Alcubierre's work and a number of different people who had been thinking about these sorts of exotic propulsion ideas for many decades, the Orion projects for nuclear propulsion back in the 70s, and all sorts of very interesting ideas that had happened in the decades in between. And that is also when I came into contact actually with this program of space physics that had just recently started. It started when I was still in high school here at Embry-Riddle. And what really fascinated me was this exotic propulsion discipline that they offer, this concentration. And so I came down to Embry-Riddle while I was still in high school. I think I was about 15 or 16 at the time, and talked with the then head of the physics department, Daryl Smith, Daryl, if you're listening to this, hi. And we talked for hours about exotic propulsion, and at that point, I was hooked and really wanted to get involved. After that, after learning more about the technical aspects of it, it became much more of a daunting task. But I still maintain an interest. And as far as inspirational words, even though I didn't pursue it necessarily right then and there, while I was at Embry-Riddle, I needed to have some patience to build up the required technical knowledge eventually. As we're seeing here, managed to make a contribution. So I would say persistence is key. So maybe I should stop talking there. Right. So I believe you can provide a link to my Göttingen address or the Gmail address that I provided in the link, the description of the video on YouTube. Correct, Erik? Sorry, I didn't repeat the question. Contact information for getting in touch about future aspirations, about future work. You can read about it. I have a website and recently started a blog about this on my website, eriklentzphd.com. You can also contact me. My contact information is on the website, lentze.phd@gmail is probably the easiest way to get in contact with me there. All right, we're good. Oh, sorry. So I'm being told we're out of time. So thank you very much, everyone, for listening. Thank you very much for all of your very thoughtful questions and comments. And hope to see you around.